Hello everyone, this is Wentao Yan from the National University of Singapore. Today, I'll talk about our work on computational modeling of microstructure evolution in additive manufacturing. So this work are mainly done by myself and my students, particularly my postdoc, Dr. Min Yang, and my PhD student, Yefeng Yu. So the overall framework of our work is focused on modeling of process structure property relationships, including the process modeling. Here, when we got the fabrication parameters, we simulate the temperature profile and void formation, and then we input into a cellular automaton and phase field models to predict grain evolutions. With this structure information, we use crystal plasticity models to predict mechanical properties, so that we can replace most of the trial and error experiments. So today I will just focus on the microstructure evolution models here. So the questions we want to answer through modeling here is, what are the grain evolutions during additive manufacturing process, including nucleation, growth like epitaxial growth and heterogeneous growth, remelting, regrowth, solid state phase transformations like grain coarsening, precipitation. And lastly, is how to refine grains like by adding nanoparticles. Second topic is to understand the defects due to solidification, like solidification pores and hot cracking. So with that, we develop a couple of models. One is the grain evolution models using the phase field method. Second is the dendrite growth model using the cellular automaton method. So for the grain evolution model using the phase field method, so these are the equations. What I want to highlight here is the driving force for the grain growth is the interface and energies. And you can see in the grain boundary mobility is dependent on the temperature. And we also incorporate the anisotropic grain boundary energy. Another thing is we actually incorporate a nucleation model in this phase field to incorporate the nucleation, but I will talk about this later. So the temperature field is actually we simulate here. We simulate the manufacturing process of 3 layers, and in each layer there are 3 tracks. So this is simulation results of the first layer first track, first layer third track, and second layer third track, third layer third track. In each layer, between each layer we have a cooling stage. And you can see the experimental results here. The multiple widths and depths agree well between the simulation and experiments. And this 3-layer, 3-track process is representative to this layer-by-layer additive manufacturing process. And for the initial grain morphology, we consider that in both the substrate and the powder particles. And you can see in each powder particle there are multiple grains. And with the temperature profile from the melting temperature, we implement into the grain growth model, and where we incorporate the nucleation model. So this nucleation model is also dependent on the temperature, so that we can incorporate the undercooling. And this model enables us to explicitly capture the nucleation site, like the pink dots here. But each nucleation site does not necessarily lead to a grain because of the growth competitive. And to look at this more clearly, this is the first layer. You can see first track, second track, and third track, and you can see the remelting. This is a then this is the second layer. You can see the remelting regrowth, but others you can see like they are mostly column grains due to epitaxial growth. And to look at the remelting and regrowth more clearly, you can see here. So this is the first track, second track, and third track. So these are the fusion boundaries. And so we can find the overlapping zone like here. We enlarge it, and you can see like this pink grain will partially remelt and then regrowth into the new track. So this is remelting and regrowth. And also here you can see this grain grain. So uh, it's it's far from the molten region, but it's become coarsening because of the heat effect. And here we statistically calculate the average grain volume in each track and layer, and you can see the grain volume is becoming larger and larger. So one is because the uh, larger column grain. Another is due to the re remelting and regrowth, and also as well as um, a coarsening. So we did experiment to validate the model. So this is the EBSD mapping from experiments, and this is our simulation results. Now you can see we can classify the grains into two types. First type, type 1 is in the overlapping region, so it's coarse grains due to the remelting and regrowth. Second type is uh, in the middle of the molten pool, they are clustered slender grains. They are actually, due to epitaxial growth, and they are column grains. And we further statistically analyze the aspect ratio distribution, and you can see the simulation and experiments agree pretty well, which demonstrates the accuracy of our model here. Um, and besides grain coarsening, precipitation is significant, especially in electron beam powered by the fusion, because the preheating temperature is pretty high. So this is the temperature curve measured in experiments, and we use this temperature profile input into the our model for precipitation, and you can see the precipitation process. And there are three stages. One is growth, and it's appear in the grain boundaries, but relatively continuously, and then it continue growth, but also decompose, so it becomes kind of isolated, and then the growth resume. So you can see in the experiments, different regions actually are in different stages, and they agree well with the simulation. After understand the grain growth in the molten pool, we want to tailor the grain structure, or especially refine the grains, because that can improve the mechanical properties. One common approach is by adding nanoparticles. So here, to explain this physical mechanism, we modify our nucleation model by setting the contact angle to be non-zero near the particles and 180 degree at other position, so that we can introduce heterogeneous nucleation on particles. And in the phase field model, we add two terms uh, which indicate the reflection, the interaction between particles and phases and grains. So the total interfacial energy is lower when the grain boundary is mixed with the particles, so that the pinning effect of the particle, nanoparticle can be introduced on the grain boundaries. So these are the manufacturing parameters we use in our simulation, which is the same with our experimental validation. So these are simulation results. We extract the temperature profile in the transverse section and longitudinal section. And in the initial grain morphology, we assume it's very fine equal acid grains because we want to simulate the steady state. So actually here, it's not just substrate, it's more of the previous layers. So this is a grain evolution in transverse section, and the particle content is 5% in volume. And you can see one is the columnar grain formed near the fusion boundary, while the equal acid grain is mostly in the interior of the molten pool. And here, we zoom in here, you can see the nucleation here in front of the solid, kind of in front of the solidification front, because the equal acid grains nucleate upon the particles within the molten pool. And finally, the equal epitaxial growth of the columnar grain is stopped by the equal acid grains by nucleation. Here is the grain evolution in the longitudinal section. You can see the columnar grains are near the fusion boundary, the same, and equal acid grains are in the interior of the track, so which confirm the observation in the transverse section. And also, the particles are distributed both inside the grains and also in the grain boundaries. So we also set different contents of the nanoparticles, so to investigate its influence on the grain morphology, like 0%, 5%, and 10% in volume. And this is the result here. And you can see this is the experimental results in the literature. Now you can see the distribution of the columnar grain and equal acid grains, and also the influence trend of the particle content all agree well between the experiment and simulation. And we do more statistical analysis here. You can see the aspect ratio at different non-particle content. You see actually the aspect ratio becomes smaller or closer to 1 with the increase of the particle content. That's because the greater grain refinement due to the nanoparticles. So in summary, you can see how the grain refinement works. So with the increase of the nanoparticle, the pinning effect will be stronger, so the grain growth will be kind of weaker, and so the supercooled region will be larger. At the same time, the nanoparticles will increase the nucleation site, so that finally the grain will become uh, smaller, will be refined. So to evaluate how the pinning effect influence the grain coarsening and also the grain structures, we conducted one simulation case with pinning and also for sure the nucleation effect. In other case, just for comparison, we deactivate the pinning effect so that you can see the results. Uh, both the uh, both the column grain and equal acid grains become a little bigger without pinning effect. So that means the pinning effect is also will also reduce the coarsening rate of the grains. So the next model is the dendrite growth model, because the dendrite growth model is related to the solidification defects. So there are a few existing dendrite models, but the critical issues are how to incorporate arbitrary orientation of the dendrites. Second is the quantitative accuracy of the simulation. So one commonly used method is called virtual front tracking method, schematically shown here. So there is a virtual solid liquid interface in the interfacial cells, and the decentered square or octahedron growth algorithm is used to calculate its movement according to the solute equilibrium condition. So the arbitrary orientation can be captured, but the quantitative accuracy is not so good because we don't really resolve the surface in the cells. So if we want to improve the accuracy, we have to refine the mesh, but which on the other hand will increase the computational cost, and sometimes it's unfeasible. Second method currently used is cell mass balancing method, schematically shown like here. In this method is to evaluate the movement of the interface by the evolution of the solid fraction in cells, and then the change of solid fraction in cell is determined by the solute equilibrium condition, like here. But the 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 method can arbitrary can have a good quantitative accuracy, but the arbitrary orientation of the dendrites is difficult to incorporate. Based on all of this, we developed a multi-grid method to simulate the dendrite growth. So first is there's a parent grid. In this parent grid, we calculate the interface movement and also the chemical element diffusion. And in the interfacial cells and also the potential interfacial cells, we remesh it into fine cells called child grid. And in this child grid, we use decentered octahedron growth algorithm. So in this octahedrons, there are virtual solid liquid interface, and the movement of the interface is represented by the growth and capture of the octahedron envelope. This is a calculation schedule here, scheme here. You can see in the parent grid we calculate the diffusion and the interface movement. And in the child grid, we capture the octahedron envelope and update the solid fraction, so that then we update the solid fraction in the parent grid. Then do this circle. With the interface advancement, which we change the we remove some of the parent, some of the child grid, and induce some new child grid in some of the parent grid. So the advantages of this method is we can achieve the arbitrary orientation easily, and second is the child grid can enable accurate evaluation of the change of solid fraction. Third is the computational cost is not significantly increased, but the accuracy is is improved by the child grid. So this simulation shows the ability of our model to simulate the growth of dendrites with arbitrary orientations. And here we also verify our model against the KGT model. You can see after going to steady state, the tip velocity agree well with the KGT model results. And also here, this is a tip velocity curve at different undercoolings. And these are our simulation results, and different curves represent the KGT model with different parameters. And you can see they agree pretty well, which verify our model. And also we extract the dendrite tip morphology in both the longitudinal cross-section and the transverse sections. And you can see this longitudinal cross-section compiles the events solution, and the shape of the transverse section agree well with the Fourier decomposition. And also we validate our model against a simple experimental case in casting. So this is X-ray imaging from literature, and you can see not only the morphology but also the dendrite growth rate agree well between the simulation and experiments. So in a real electron beam powered by the fusion process experiments, we do the validation. So first simulate, the melting process with a thermal fluid flow model, and then we extract the solidification conditions at different regions, 1, 2, 3, and at different regions the temperature gradient, cooling rate are different. Then we simulate the dendrite growth at different regions. So these are the simulation results. This is the experimental results. So there are two critical issues. One is the primary dendrite arm spacing. So you can see we do the statistic analysis in both experiment and simulation, and you can see at different regions they agree well. And second critical issue is the niobium distribution. So this is a experiment and this is a simulation. We extract along a curve and then extract the niobium distribution. You can see the peaks and valleys. The peaks, in both simulation and experiments show similar patterns. And next question we want to answer after simulating dendrite growth is how the shrinkage pores form. Okay, basically people know the shrinkage pores are formed because the material shrinkage during solidification cannot be fed by the liquid, and this is commonly seen in additive manufacturing, and it can potentially nucleate the cracking and reduce the fatigue life of the components. But actually there are two types of shrinkage pores in additively manufactured nickel-based superalloy. One is a shrinkage pores between dendrites. Another is the shrinkage pores at the grain boundaries. So they have different shapes. So essentially they have different formation mechanisms. But previously, people just use one physical mechanism to explain these two types of pores, which may not be accurate. So this is a simulation results at different misorientations, 0 degree, 10 degree, and 20 degree, and this is the cooling rate and temperature gradient. And this is the simulation results. You can see, the formation process of the shrinkage pores can be different. And this is with no misorientation. In the beginning, it's like pipes, pipe shape, and in the and eventually it will become relatively spherical. And for the dendrite growth with misorientation, it's not a pipe-like geometry, and the shrinking pulse can be irregular. We'll talk about it later here. So the underlying physics is, the pipe shape remaining liquid will further solidify from the bottom to the top. So the liquid feeding suffer resist, but the liquid feeding suffer resistance because the temperature is already low. So the viscosity is become higher and higher. So that in some cases cannot fit. So the shrinkage pulse will happen. So, but in this case, mostly it's spherical pulse. And for the pulse formed between dendrites with misorientation, you can see these isolated regions will lead to shrinkage pulse, and they are mostly irregular shape and appear with solute-rich precipitates. So we further investigate the case with different cooling rates and different misorientations. So these are the simulation results and different cooling rates: 2000 K per second, 5000 K per second, 10,000 K per second, and you see the primary dendrite arm spacing is smaller and smaller with the increase of the cooling rate. And for the mechanics 1, without misorientation, you can see with the increase of the cooling rate, the shrinkage pulse becomes smaller and smaller. And for the second mechanism with misorientation of 20 degree, you can see also the shrinkage pulse becomes smaller and smaller. So finally, we want to add one comment is our previous models are mostly focused on the polymer fusion, like laser polymer fusion or electron beam polymer fusion. But actually, for other additive manufacturing techniques, like direct energy deposition, this we also have the thermal fluid flows models, so that we can get the relatively reliable temperature profile. And if we implement this temperature profile from these models to our existing growing growth, dendrite growth models, we can also solve the problem in this direct energy deposition process. So that it means actually this microstructure evolution model is pretty generally applicable in this additive manufacturing field. And due to time limitation, I may not be able to explain all the model details very well. So if you are interested, you are suggested to read the papers by us. So with that, I want to thank you all for your listening, and that's all of my presentation.